Okay, so we're starting with structures of ionic bonding. This one's actually really simple because all you have to do is show the electron transfer from whatever is giving up electrons to whatever is gaining electrons. So for example, we're going to use NaCl whenever you react a sodium with a chlorine and they are combined. It's actually a very powerful reaction because sodium really wants to give up an electron and chlorine really wants to take on electrons. So the way that we show this using Lewis dot symbols is this is sodium's regular uncharged Lewis dot structure. This is chlorine's regular uncharged Lewis dot structure. It has 7 valence electrons. Sodium had 1. So what happens is 1 valence electron moves from sodium to chlorine. And now we have a sodium ion, which we represent as Na+. And we have a chloride ion, which now has 8 dots around it. And we represent that as Cl-. You'll see these brackets sometimes, but for right now, those aren't that important. Okay. So this is how we show the formation of an ionic bond, or really how ions form, and then they can attract with their positives and negatives. So in example number 1, I want you to show the formation of the ionic compound CaF2, just that one because there's not enough space for Li2S, using Lewis dot structure. So what I did is I first drew calciums and fluorides structures. So hang on. Okay. So this is calcium's regular plain old Lewis dot structure, and this would be fluorine's regular plain old Lewis dot structure. Fluorine has 7 valence electrons, so I represent them like this: pair, 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 1. Same thing. I did 2 fluorines because it's CaF2. Now there's a reason for that, okay? So if you're looking at this, what's going to happen is calcium has 2 valence electrons, so it's closer to 0, so it's going to give up its 2 electrons. Fluorine has 7, which is closer to 8, so it wants to take in electrons. So what's going to happen is one of these valence electrons is going to go over this fluorine. One of these valence electrons is going to go over this fluorine. Now calcium will have lost both of its valence electrons, so it's happy. It's got a full octet in the level under. So we represent that as calcium 2+, and I have 2 fluoride ions that now have 8 around them, and they are -1. So you'll see that the charges all work out. So that is what's really going on with the electrons when we're talking about ionic bonds. Okay, so they transfer. I have a positive and I have 2 negatives now. They attract each other, and then they form what is called a crystal lattice. Okay, so ionic compounds look like this. Okay, you get the positives and the negatives interdispersed, and they are attracted to each other because they're positives and negatives. This is what NaCl looks like in its crystal structure. Okay, so now I'm going to talk about regarding these what's called lattice energy. And that is the energy that's required to break an ionic bond, or the bond between that positive and negative. So how hard is it, or how much energy does it require to break a bond between a sodium and chlorine? That's really what lattice energy is. Well, we know based on Coulomb's law, if you remember back to Coulomb's law, the closer things are together and the more charged they are, the stronger their attraction. So we would assume that lattice energy is going to increase with things that have stronger charges, so like +2 versus +1, or if they are closer together. So really atoms that have smaller radii. So if they're smaller, they're going to be closer together, harder to break apart. So those are the 2 things that actually affect lattice energy. It is first and foremost the magnitude of charge, because that affects it the most. So like I said, a +1 versus a +2, a +2 is going to have more attractions. Okay, so more attraction means higher lattice energy. It is generally the more important one. Okay, so you want to look for larger charges first, and then say they have the same charges, say they're both +1, -1. Then you're going to look at how big the nuclei are. So smaller radii, so if it's more up and to the right on the periodic table, they are going to be closer together. So they're going to have more attraction, have a higher lattice energy. So I'm going to show you how that works down here. If they all have the same charges, so LiCl, NaCl, KCl, and CSCl, all of these have a +1, -1. And you'll notice that the lattice energy, this one gives off the most energy, or requires the most energy in order to break that bond. Kind of ignore the negative for right now. In order to break this LiCl bond, that is the reason that this one is the hardest, or has the most energy associated with it, is because lithium is smaller than sodium. So if we look at our periodic table, let me pull that up really quick. And here I got the periodic table. So I've got lithium, sodium, potassium, and I think the other one was cesium. So as we go down, remember, they get bigger. So cesium you could think of as this big old atom trying to attract a chlorine, whereas lithium is this little atom trying to attract a chlorine, and they're all attracted to that chlorine. So if I go back here, we've got that lithium chloride has the highest amount of lattice energy because it is the smallest. Here's a representation of their sizes. These ones have a smaller radius because lithium is smaller than cesium, so it makes it harder to break. Okay, so lattice energy has to do with the charges and then how close they are together. So what I recommend doing now is doing the second example on this next page and then checking your answers. Okay, so example number 2 says to rank in order of lowest, that means the easiest to break, to highest lattice energy, or the amount of energy associated with breaking that bond, the following 4 compounds. So I have NGO, KCl, Na2S, and BAS. Now I told you that the most important thing regarding lattice energy is the size of the charge. So we check those first, okay? Mg and O, those are +2, -2. K and Cl are +1, -1. Na2S, well, Na is +1 and S is -2. And BAS, you've got +2 and -2. Now, how did you know those? Well, if you look back at the periodic table, everything in column 1 likes to be +1. Everything in column 2 likes to be +2. Skip the middle. +3 over here. This one can go either way. Then -3, -2, -1. Okay, this is something we talked about a while ago. But the higher charges are going to have the strongest attraction or the highest lattice energy. So MgO and BAS are going to be highest, and then Na2S and then KCl. So I said list from lowest to highest. So KCl is going to be the easiest one to break because it's only +1, -1. Next will come Na2S because we got a +1 and -2. Now, if these are both 2, so I got +2, -2, and +2, -2, then we have to look at the size. Okay, so I've got MgO and BAS. So I go back to my periodic table and I'm like, okay, I got Mg and O. I've got BA. Well, BA is bigger, and S is also bigger. So if I've got BAS, we know that the radii are larger. So we go back to the question. If they have a larger radius, they're going to be a little bit further apart. So they are going to have less attraction, which makes them easier to break. So BAS should be next. And then MgO that has +2, -2, and the smaller of the 2 radii is going to have the highest lattice energy.